Usually when we talk about a medical diagnosis, there's this like underlying expectation of absolute precision. It's almost like engineering.
Right. Yeah, it's binary.
Exactly. Like you break your arm, you go to the hospital, and the X-ray shows that jagged white line on the black film,
Mm.
and the doctor just points at it and says, there it is.
It's definitively broken or not broken.
Yeah.
It's comforting, honestly. We humans really like things to be visible and easily categorized.
We want them in neat little boxes.
Yeah.
But then you step out of the hospital and into the world of evaluating a beautiful, faceted gemstone, and suddenly that metaphorical X-ray machine is just, well, it's completely broken.
Oh, absolutely shattered. You're looking at a diagnostic landscape that is, honestly, incredibly murky.
It really is. And it's this high-stakes arena where literally millions of dollars change hands on a daily basis.
Right.
But historically, those transactions have been based on, like, highly subjective human vision.
Right, human vision and just historical accidents in naming conventions. Not to mention the completely invisible chaos of atomic structures.
It's the absolute definition of diagnostic muddy waters. Welcome, everyone, to today's deep dive. We are so thrilled to have you here.
We really are. And frankly, the financial stakes in the global gemstone market demand a level of rigorous, reproducible science that the industry has historically struggled to provide.
Yeah, for centuries, it was way more art and folklore than chemistry and physics. And when I say you today, I mean you, the amateur historian, the gem enthusiast.
The person who looks at a glittering museum display and doesn't just see a pretty rock. You want to know the geological violence.
Exactly. The rigorous microscopic science that brought that specific stone to that specific glass case. Today, our mission is to examine a monumental piece of work.
We're digging into the Color Encyclopedia of Gemstones, 2nd edition by Joel E. Arem. It is a foundational text.
It really is.
Yeah.
It doesn't just list pretty rocks and their origins. It fundamentally attempts to drag gemology kicking and screaming into the modern scientific era.
It demands that we look at these stones strictly through the lens of empirical data.
Now, because we know your background, we're going to set some ground rules for today's deep dive. We know you aren't starting from zero.
Right, we're completely skipping the basic definitions today. We know you already understand what a carat is or what a facet is.
You know the crown and pavilion of a cut stone. So instead, today, we're going to act as your pedagogical coaches. We're going to treat this like a masterclass.
We'll be moving systematically through the core concepts of Arem's work, and we'll be leaning heavily into the industry-specific terminology.
The actual terms that working gemologists, mineralogists, and crystallographers use in the laboratory every day.
Okay.
Our goal is to equip you with the advanced mental models required to evaluate these materials.
Not just as historical ornaments or symbols of wealth, but as incredibly complex data sets of chemical, optical, and thermal properties.
We want to change the way you look at a gemstone forever. To do that, we've structured this deep dive very deliberately. We are using a strict chapter-by-chapter framework.
Right. For each chapter, we're going to make sure we hit the absolute core thesis first, the big idea. Then we plunge into the advanced technical nuances.
The real how and why. Then we'll build the connective tissue, showing you how a chemical property dictates an optical one and how that impacts market value.
And we will make sure you walk away with highly practical, actionable takeaways, a practical recap for your own research.
Finally, we'll leave you with a critical thinking challenge. Real-world scenarios to test your application of this highly technical material. Okay, let's unpack this. I want to start by looking at Chapter 1.
Ah, yes. The very origin of these stones. What Arem essentially frames as the geological lottery.
It's the perfect place to start. So let's get the big idea for this first chapter.
If we distill this initial concept down to its core thesis, it is this. A gemstone's true value and its proper classification are intrinsically tied not to subjective, historically loaded terminology, but to its definite crystalline structure, its incredibly complex chemical variations, and its extreme geological rarity.
Wow, okay. Let's get deeply into the advanced deep dive of those nuances. And I want to start by throwing out some terminology that you, as a historian, have probably seen everywhere.
You're talking about the words precious and semi-precious, aren't you?
Exactly.
Right.
If you look at historical texts, going all the way back to Pliny the Elder, or ancient Sanskrit texts, or even the Bible, we see these terms thrown around constantly.
They're used to designate inherent value, but Arem's text makes a very aggressive, very necessary point here. These terms are entirely obsolete.
They represent a time before gemological science even existed. which has led to incorrect names and false hierarchies that have stubbornly persisted for over 2,000 years.
It is a crucial starting point for anyone serious about this field. The terms precious and semi-precious are artifacts of a completely subjective human hierarchy.
Right. They're not a geological reality.
Exactly. Historically, precious was reserved for diamond, ruby, sapphire, and emerald, and literally everything else was lumped into semi-precious.
But the text points out a startling economic reality to thoroughly debunk this outdated system. In the modern market, you can purchase a low-grade diamond, the ultimate precious stone, for, like, what?
For as little as $200 a carat in some cases.
Which is practically nothing in the gemstone world.
Precisely. Meanwhile, certain specific varieties of garnet, a stone that has historically been relegated to the lower tier semi-precious category, are currently selling for well over $1,000 a carat.
Sometimes even several thousand, right? We're talking about stones like vivid green savorid or fiery demantoid garnet.
Yeah, exactly. It completely inverts the old historical hierarchy. You have a quote-unquote semi-precious stone outvaluing a precious one by a factor of 5 or 10.
So if we, as modern researchers, must abandon those terms completely, what actually replaces them? How do we scientifically define what we are looking at?
Well, we have to look past the macro appearance. We have to dive into the mineralogical nuances, specifically the concept of the solid solution series.
Right, solid solution series. Let's unpack that.
You see, the chemical composition of a mineral isn't always a rigid, unchanging recipe. It's not like pure water being strictly H2O.
In many mineral groups, the chemistry varies, but it varies within highly defined structural limits. Let's make sure we really grasp this.
Sure. Think of it like a slider on an audio mixing board. On one end, you might have a mineral where a specific structural site is filled 100% by iron.
Okay, so that is one end member.
Yes, and on the far opposite end, that exact same structural site is filled 100% by magnesium. That is the other end member.
But in nature, a stone rarely forms at those absolute extremes, does it?
Exactly, no. It forms somewhere in the middle. It's a mixture. It's a structural hybrid.
But humans need to categorize things. We can't just call it a mostly iron, somewhat magnesium thing. So how does the scientific community decide what to actually call it?
In the case of a simple two-component solid solution series, mineralogical convention dictates a strict, mathematically rigid dividing line. It's called the 50% composition rule.
Ah, okay, so it's a literal halfway point.
Yes. If a mineral's chemical variation crosses that exact 50% threshold, say it goes from being 49% iron to 51% iron, it formally becomes a distinct new mineral species.
With an entirely new scientific name. It ceases to be mineral A and officially becomes mineral B.
Standard gemologists sometimes overlook this incredibly dense mineralogical literature. They prefer to just look at the color, but this 50% rule is the absolute bedrock of proper classification.
It is especially critical when dealing with incredibly complex groups, like the garnets or the feldspars, right? Where solid solution is the rule, not the exception.
Absolutely. Which brings us down to the atomic level. Because this isn't just a clean sliding scale of one ingredient replacing another perfectly in a pristine laboratory.
The text talks about atomic substitution. And this is where the sheer geological chaos of the Earth really shines through.
The geochemical environments where these crystals grow deep underground under massive heat and pressure are incredibly messy.
You have a multitude of different elemental atoms all floating around in this hot chemical soup, all competing for structural sites within the growing crystal lattice.
Yes, and the rules of who gets to sit where in that lattice are governed by physics. These structural sites within the crystal can be remarkably accommodating to different elements.
But they're also highly specific about the electrical charge, right? And the physical size, the ionic radius of the atom trying to fit in.
Precisely.
I like to think of it as a microscopic, high-stakes game of musical chairs played by atoms. Let's take the text example of the mineral diopside.
That's a great example to use here.
Now, the ideal textbook chemical formula for diopside is calcium magnesium silicate, CamGSi 206. That is what it wants to be.
But in the real world, in the chaotic soup of the Earth's crust, the music stops and the atoms scramble for a seat, you might have an atom of sodium substituting for the calcium.
But sodium and calcium don't have the same electrical charge. So to keep the whole crystal electrically neutral at the exact same time, an atom of titanium is jumping into the seat meant for magnesium.
And An atom of aluminum is aggressively shoving silicon out of the way.
It is a beautifully chaotic picture. All of this is happening simultaneously in varying unpredictable amounts within the exact same crystal structure.
That is a highly accurate analogy, and what's fascinating here is how this atomic game of musical chairs directly, measurably impacts the physical properties of the final stone.
A parameter like refractive index, how much the stone bends light, is exquisitely sensitive to these tiny variations in chemical composition.
Exactly. Iron is a heavy element. If it substitutes for a lighter element like magnesium, the density of the stone increases and the refractive index shoots up.
When you have sodium, titanium, and aluminum all crashing the diopside lattice simultaneously, correlating the resulting changes in physical properties with those compositional variations becomes an incredibly complex puzzle.
It really is a massive mathematical and scientific puzzle.
So we have this chaotic chemical substitution happening within a strict crystalline structure. But that still doesn't quite explain why some of these resulting stones are so mind-bogglingly expensive.
Right, because, quartz has impurities too, and it's dirt cheap.
Exactly. So let's talk about geochemical rarity, because it's not just about the internal structure, it's about the sheer statistical improbability of certain chemical ingredients even being in the same geographical room together.
The quintessential example provided in the text to illustrate this is emerald. Emerald is the highly prized deep green variety of the base mineral beryl.
Now, beryl itself, as a mineral species, is not exceptionally rare, is it?
No, it occurs all over the world, predominantly in specific geological formations called pegmatites.
Right, and just to give our listeners a visual, pegmatites are essentially the last watery, mineral-rich juices of a cooling magma chamber. They crystallize slowly, allowing for massive crystals to form.
And common beryl from these pegmatites gives us beautiful but relatively affordable stones like the blue aquamarine or the purely colorless goshenite.
But emerald is fundamentally different.
It is different because of a single, highly specific trace element, chromium. Chromium is the atomic ingredient responsible for that incredibly intense, highly prized, vivid green color that defines a true emerald.
Here's the geological catch and the root of its immense value.
Yeah.
Chromium is geochemically foreign to pegmatites.
It absolutely does not belong there. It's from a different neighborhood entirely.
So where does it come from?
Chromium is typically concentrated in ultramafic rocks, dark, heavy rocks formed deep in the Earth's mantle. These are completely segregated from the lighter, silica-rich pegmatites closer to the surface.
So for an emerald to form, you need the sheer geological accident of these two entirely incompatible geochemical environments colliding.
You need tectonic violence, you need hydrothermal fluids from a beryllium-rich pegmatite to somehow physically slice through a chromium-rich schist or ultramafic host rock.
Under the exact right conditions of heat and pressure. The value of the emerald, therefore, isn't just in its visual beauty. It is a direct financial reflection of its extreme geological scarcity.
It's like finding a polar bear in the middle of the Sahara Desert.
That's a perfect metaphor. The environment is completely wrong, the core ingredients are wrong, but somehow nature violently forced them together to create this absolute anomaly.
The stone is literally a record of an improbable geological event.
Okay, so let's tie all of this together with the connective tissue before we move to the next chapter. We've established that a gemstone's true identity, its true scientific name, lies in its invisible chemical variations.
Right. It's placed on a solid solution series, and these highly accidental trace elements like chromium.
Because all of this intense chaos is happening strictly at the atomic level, visual identification with the naked eye, or even a basic jeweler's loupe, is wildly, hopelessly insufficient.
You absolutely cannot see the 50% mathematical split in a solid solution series with your eyeball.
This physical limitation sets up the absolute necessity for the advanced objective diagnostic tools we are going to explore next.
Exactly. We must move away from historical visual estimation and move firmly into the realm of empirical data collection.
So let's get into the practical recap for this chapter. As an historian or a researcher taking notes, here are your actionable takeaways. Number 1. You must permanently abandon the terms precious and semi-precious in all your gemological evaluations.
They are economically false and scientifically meaningless.
Number 2. You need to start evaluating gems as distinct crystalline structures that are constantly subject to complex, solid solution variations, always keeping that strict 50% dividing rule in mind.
And number 3. Recognize that extreme rarity, and therefore the astronomical financial value, often stems from the highly unlikely intersection of incompatible geochemical environments.
Just like beryllium and chromium forming emerald. Which leaves us with a real intellectual puzzle for you to chew on. Here is your critical thinking challenge for Chapter 1.
Imagine you are working in a laboratory. Question 1. How would you formally classify a newly discovered mineral variation that sits exactly at a 49 to 51% split within a solid solution series, keeping in mind that the margin of error in chemical testing equipment might be 2%?
Which side of the line does it truly belong on? That margin of error question is a nightmare for a taxonomist.
It really is. And question 2, if a historically abundant so-called semi-precious stone is suddenly found in a geochemically rare color due to a freak, anomalous trace element inclusion, how does that singular discovery disrupt traditional, centuries-old historical valuation models?
Take some time to ponder the economic chaos that would cause.
Next. All right, Chapter 2, the arsenal of identification.
How do we actually extract this invisible data? Let's get the big idea for this chapter.
The core thesis here is this. Reliable, indisputable gem identification requires looking entirely beyond surface color by utilizing advanced, non-destructive optical, spectral, and thermal measurements to uncover the stone's unique internal atomic signature.
Let's dive deep into this arsenal. And here's where it gets really interesting, because we are operating under a massive, unyielding constraint in gemology.
We absolutely cannot destroy or damage the sample.
If a field geologist wants to know exactly what a chunk of granite is made of, they crush it into a fine powder, they dissolve it in a beaker of hydrofluoric acid, and run a complete chemical analysis on the liquid.
We obviously cannot do that to a flawless 10-carat ruby.
We have to somehow interrogate the internal structure of the stone without leaving a single microscopic scratch on its polished facets. Let's start with thermal properties.
Thermal testing is highly attractive to gemologists because it's entirely non-destructive. And the required instrumentation can be relatively affordable and portable.
We're essentially measuring how heat energy transfers through solid crystalline materials at room temperature, which happens primarily via conduction.
But when we look at the specific thermal properties that are physically available to measure, like specific heat or thermal conductivity, they present severe practical challenges for a quick, reliable diagnostic test.
Right, let's break that down. Specific heat is, definitionally, the amount of heat energy required to raise exactly 1 gram of a substance by 1 degree Celsius.
But Arem's text notes that this specific metric varies very little among the vast majority of common gem minerals. A ruby and a sapphire and a spinel might have nearly identical specific heat capacity.
So it's a terrible fingerprint.
Exactly. It doesn't give you a clear enough differentiation. That is why a different property, thermal inertia, emerges as the most practical, highly sensitive measurement for gemologists in the field.
Thermal inertia essentially measures how quickly a material's surface temperature changes when it is suddenly subjected to a localized heat source.
It is not just one property. It's a complex mathematical combination of the material's thermal conductivity, its physical density, and its specific heat capacity all working together.
So how do we actually measure that without damaging the stone?
We use a simple handheld thermal probe. The tip of the probe is heated to a known temperature.
When you touch it to the facet of a room temperature gemstone, the heat rapidly flows from the probe into the stone.
Because different minerals have vastly different thermal inertias, the rate at which the temperature of the probe tip drops is highly variable.
The internal circuitry measures that minute drop in temperature. It is incredibly diagnostic.
Especially for separating true diamond, which has an anomalously high thermal conductivity from its many visual simulants like cubic zirconia or glass.
Okay, so we can test how the atomic lattice handles the flow of physical heat. But what about how it handles the flow of light? I want to talk about dispersion.
Dispersion is fascinating.
We all know that when a beam of white light enters a faceted gem, it slows down and bends. That's basic refraction. But because white light is made of different colors, those different wavelengths of light bend by slightly different amounts.
Right, separating the white light out into a spectral rainbow, that separation is dispersion.
But dispersion sounds like a subjective term. How do we actually scientifically measure that rainbow so we can compare a diamond to a zircon on a spreadsheet?
We have to use a highly standardized, globally recognized metric. By scientific convention, the optical dispersion of a gemstone is defined as the mathematical difference in its refractive index, measured at 2 very specific, universally constant wavelengths of light.
We use what are called the Fraunhofer spectral lines, right?
Right.
Specifically the B and G lines. Let's pause and explain those.
Sure, these are the dark vertical absorption lines seen when you look at the continuous spectrum of our sun, discovered by Joseph von Fraunhofer in the 1800s.
The sun emits a continuous spectrum of light, but certain elements in the sun's outer atmosphere absorb very specific, incredibly narrow wavelengths.
This leaves dark gaps, the Fraunhofer lines, in the rainbow we see on Earth. Because these gaps are created by fundamental atomic physics in the sun, they are absolute, unwavering constants.
The B line sits deep in the red portion of the visible spectrum, at an exact wavelength of 6,870 angstroms.
And the G line sits in the blue portion of the spectrum, at exactly 4,308 angstroms.
And just a quick reminder, an angstrom is an incredibly tiny unit of measurement used for wavelengths of light. 1/10,000,000th of a meter.
Exactly. So to calculate dispersion, a gemologist must measure the stone's refractive index using purely red light exactly at the 6870 angstrom B line.
Then they measure the refractive index again using purely blue light exactly at the 4308 angstrom G line.
By calculating the mathematical difference between those two distinct measurements, we arrive at a dimensionless number. That single precise number is the stone's official dispersion value.
It completely strips away the romantic, highly subjective visual experience of a diamond's fire and replaces it with cold, hard, reproducible optics. I absolutely love that.
It takes the poetry and turns it into math.
Exactly. Taking a diamond, throwing flashes of rainbow fire across a dimly lit room, and turning it into a strict mathematical interval between the B and G solar absorption lines. Now, speaking of how light behaves inside the crystal lattice, let's talk about pleochroism.
Pleochroism. This is the phenomenon where a single stone actually shows completely different colors depending on which crystallographic angle you view it from.
Arem's text notes that pleochroic colors are strictly reported across the X, Y, and Z optical axes of the crystal. But I have a major question about this.
Okay, what's the question?
The text mentions isotropic materials. By definition, isotropic materials like the garnet group or the spinel group have a perfectly symmetrical cubic crystal structure.
Right, they do.
Because it is perfectly symmetrical, light should theoretically travel through them at the exact same velocity in all directions. Therefore, they shouldn't exhibit pleochroism at all. They should be just one solid color no matter how you twin them.
Right. Theoretically, yes. According to textbook physics, an isotropic material should absolutely not show pleochroism. But here is where the messy, violent reality of geology fundamentally complicates the pristine physics of the textbook. Sometimes, a theoretically isotropic material will display anomalous, unpredictable colors when viewed under the polarized light of a polariscope.
But how is that physically possible if the internal atomic structure is perfectly symmetrical?
Because the reality is, the structure isn't perfectly symmetrical anymore. These anomalous colors are a direct result of internal structural damage. They are often attributed to severe internal strain.
Imagine that garnet crystal growing perfectly, but then, millions of years later, it is subjected to immense localized tectonic pressure.
The crystal doesn't break, but the immense pressure physically warps and bends the atomic lattice at a microscopic level.
It's literally bending the symmetry out of alignment.
Exactly. And even more fascinating, there is abundant crystallographic evidence that this anomalous pleochroism can also be caused by the highly ordered rather than random arrangement of specific trace atoms on certain crystallographic sites as the crystal grew.
It represents a localized, permanent breakdown of that perfect cubic symmetry, revealing the hidden, violent stresses of the stone's deep geological history. It's quite literally like a geological bruise.
That's exactly what it is. The stone looks perfectly flawless on the outside, but when you hit it with polarized light, it reveals the internal trauma it suffered deep in the earth millions of years ago. It is an incredibly powerful diagnostic clue.
Okay, let's look at one more tool in this non-destructive arsenal: luminescence. Shining invisible ultraviolet light on a stone in a dark room and watching it suddenly glow in neon colors.
It's not just a cool party trick, though. As Arem's text makes clear, it's a precise chemical reaction happening at the electron level.
Certain electrons within the gemstone's crystal structure can absorb the high-energy, invisible UV radiation. This energy excites the electrons, bumping them up to a higher energy state.
But they can't stay there forever. When they fall back down to their normal state, they release that excess energy.
However, some energy is lost as heat in the process, meaning the energy released has a longer wavelength than the UV light absorbed. This longer wavelength falls into the visible spectrum, creating the glow.
If the release of light is immediate, we call it fluorescence. If the electrons get trapped and release the light slowly over seconds or minutes, we call it phosphorescence.
In gemology, we rigorously test this using two highly specific, standardized wavelengths of UV light. Long-wave UV at exactly 3760 angstroms and short-wave UV at exactly 2587 angstroms.
And what actually triggers this reaction? Because, as anyone who has played with a blacklight knows, not every stone glows. A lot of them just sit there looking dark purple.
If we connect this back to the atomic chaos we discussed earlier, the glow is almost rarely caused by the base, pure mineral itself. Pure corundum doesn't glow.
The luminescence is usually triggered by a specific trace impurity in element that forces its way into the lattice and acts as a localized activator.
Manganese is a classic, highly efficient activator in many gem species. If manganese is present in the crystal lattice in the right structural sites, it often causes the stone to fluoresce brilliantly under the UV lamp.
But, and this is a crucial diagnostic nuance that Arem emphasizes, there are also elements that do the exact opposite. There are quencher elements.
Right. The text specifically calls out iron as an incredibly aggressive quencher of fluorescence.
Exactly. Iron fundamentally disrupts the electron excitation process. Instead of allowing the energy to be released as visible light, the iron atoms absorb the UV energy and dissipate it entirely as microscopic heat within the lattice.
If a stone contains significant amounts of iron, that iron will actively suppress or completely kill any potential fluorescence.
Even if a powerful activator like manganese is sitting right next to it in the crystal structure. Therefore, the complete absence of fluorescence in a gemstone species where you might normally expect it can be just as powerfully diagnostic as the presence of a brilliant glow.
It tells the gemologist, without a shadow of a doubt, that iron is likely dominating the internal chemical environment. So an inert, dark stone under a UV lamp isn't a boring stone.
It's a stone practically shouting at you about its massive internal iron content.
It's brilliant. Okay, let's pull all these threads together to find our connective tissue. We now have this incredible, non-destructive scientific arsenal at our disposal.
We can measure the precise thermal inertia using a heat probe. We can mathematically calculate the optical dispersion between the Fraunhofer B and G solar lines.
We can spot deep atomic strain and geological trauma using polarized light. And we can map the unseen presence of trace elements like manganese and iron using the specific physics of UV luminescence.
We can scientifically, indisputably identify the hidden atomic makeup of a stone without scratching it. But here's the massive problem that the industry faced next.
How do we scientifically communicate the look of that stone to the global market?
When a wholesale buyer in New York is on the phone with a dealer in Bangkok, and they want a very specific, highly saturated pigeon's blood ruby, how do they objectively agree on what that color actually is?
Especially when human eyes and human brains are so notoriously deeply subjective. This sets us up perfectly for the next chapter. But first, our practical recap.
Number 1. As a modern evaluator, you must utilize thermal inertia over outdated concepts like specific heat or simple thermal conductivity for rapid, non-destructive field testing, especially when dealing with diamond separation.
Number 2. When you are interpreting UV fluorescence under both the 3660 and 2587 angstrom wavelengths, never just look for the glow.
Always look for the chemical interplay between potential activator elements like manganese and aggressive quencher elements like iron.
Number 3. Always rely on absolute measurable data like spectral absorption lines, such as chromium's distinct far red lines in emerald, and internal optical strain,
rather than relying on external subjective surface color for your definitive gem identification.
And your critical thinking challenge for this diagnostic section. Question 1. If a theoretically isotropic stone exhibits strong, undeniable, anomalous pleochroism under a polariscope, what specific historical or geological stress events might you deduce about its formation environment deep in the earth?
Question 2. Imagine you are presented with a stone suspected to be so heavily laden with internal iron that absolutely all UV fluorescence is quenched, rendering your UV lamp completely useless.
How would you design a multi-step, entirely non-destructive testing protocol using other tools to verify its identity? You really have to think like a forensic detective with these materials. Next.
All right, Chapter 3, the science of color. We have to address that massive communication problem we just mentioned. How do we measure the unmeasurable?
Let's start with the big idea for this chapter.
The core thesis driving this entire chapter of Arem's work is revolutionary for the trade. It is this. The global gemstone industry is being forcefully compelled to abandon archaic, highly subjective color terminology in favor of objective, machine-generated, three-dimensional colorimetry in order to completely standardize global valuation and communication.
So what does this actually look like in practice? Let's get into the deep nuances of color measurement.
For decades, gemologists have tried to solve this with simple color charts. You know the ones. You hold the faceted gem up to a little printed square of color in a heavy binder or book.
And you squint under a desk lamp and say, yep, it matches this square, we'll call it a 5B. But Arem is brutally, unapologetically clear here.
These two-dimensional printed color charts are a catastrophic, fundamental failure for the gemstone industry.
They are a failure because they are fundamentally physically incapable of representing the optical reality of a crystalline gemstone.
A color chart in a book is made of opaque ink or paint printed flatly on paper. The light hits the opaque ink and reflects back into your eye.
A gemstone, however, is a three-dimensional, highly transparent medium. It doesn't just reflect light off its surface.
It actively bends the light as it enters, breaks it apart through dispersion, bounces it around internally off the pavilion facets, and then returns it to the eye.
You absolutely cannot replicate the vividness, the inner glowing brilliance, or the physical transparency of a fine, unheated sapphire with flat ink on paper. It's physically impossible.
Furthermore, standard opaque colors printed on paper simply cannot be manufactured to reach the extreme neon saturation ranges that vivid gemstones naturally possess. The gamut of paper printing is too small.
And even if they could somehow match the saturation, the 2D charts fundamentally fail to account for the pleochroism we just discussed.
The fact that the stone might literally be projecting three entirely different colors at once, depending on the angle you hold it, trying to match a highly pleochroic transparent gem to a flat, opaque square of paint is a completely futile exercise.
It is scientifically invalid. So, if the 2D charts are out, what is the alternative? We have to move into a 3D color space.
The text discusses standardizing gemology around complex systems that are already heavily utilized in precision industries like textiles, automotive paint, and plastics manufacturing.
We're talking about defining color, not with a name, but using three specific mathematical axes: hue, value, and chroma.
Let's define those carefully. Hue is the actual color family, the foundational red, blue, or green. Value is the lightness or darkness of that specific hue, ranging from black to blinding white.
And chroma is the saturation or vividness, ranging from a dull, washed-out gray to a pure neon intensity.
The famous Munsell color system uses this physical model, but to really get objective, to truly remove the human eye from the equation, we must move to abstract mathematical spaces plotted by machines.
Specifically the Scilab system, which is often just referred to in the trade as L star, A star, B star, or just lab. Let's unpack the math of lab because this is where the precision really happens.
It's a three-dimensional Cartesian coordinate system for color. In the lab system, the L-axis represents absolute lightness.
It runs vertically from 0, which is pure, absolute black, to 100, which is a perfectly diffuse white.
The A-axis represents the green to red spectrum. It runs horizontally. Negative A values dive into deep green, while positive A values move into intense red.
Finally, the B-axis represents the blue to yellow spectrum. Negative B is pure blue, positive B is pure yellow. It's a brilliantly elegant system.
By assigning a highly specific numerical value to each of these three intersecting axes, you can plot absolutely any color the human eye can see in a three-dimensional mathematical space with pinpoint, reproducible accuracy.
You are taking a vague, poetic term like a cornflower blue sapphire and turning it into a very specific GPS coordinate in mathematical color space.
But obviously you can't calculate lab coordinates with your eyeballs. You need specialized hardware.
And I want to really geek out over the technology Arem mentions here because it's a fascinating engineering problem. He talks extensively about the Minolta portable colorimeter,
which was seen as a huge step forward because it was finally affordable for a standard gem lab. But it was absolutely not built for transparent gems out of the box.
A researcher named Dr. Richard Pettijohn had to radically modify the hardware.
Yes, the standard commercial colorimeters from companies like Minolta are designed to measure flat, completely opaque surfaces, like checking the color consistency of a painted car door.
When you put a faceted, transparent gem over the machine sensor, the light scatters wildly and unpredictably due to the angles of the facets.
Dr. Pettijohn realized the hardware had to be adapted. He significantly reduced the size of the light beam to target a very specific, isolated area of the gem, trying to avoid the facet junctions.
And crucially, he added a specialized glass plate to precisely control the physical presentation and orientation of the stone relative to the sensor.
But even with Pettyjohn's brilliant modifications, Arem notes it still wasn't perfect. He contrasts the modified Minolta with a much more accurate, much more expensive industrial system.
The Reynolds-Hale integrating sphere and fiber optic system. The integrating sphere is a massive leap in optical measurement technology. Let's explain what that is, because it's fascinating.
An integrating sphere is essentially a hollow cavity, perfectly spherical, with its interior coated in a highly reflective, perfectly diffuse white material, usually barium sulfate.
When you place the gem at the port of the sphere and shine light through it, the light that comes out of the gem bounces around the inside of that white sphere thousands of times.
This completely scrambles and integrates all the directional light beams into one uniform, homogeneous wash of light. It captures the total transmitted light from all angles simultaneously,
Creating a much more holistic, accurate measurement of the gem's overall color, rather than just measuring one tiny spot. Furthermore, these high-end systems utilize specific standardized light sources.
known as illuminance A and C. Illuminant A mathematically represents the warm spectrum of typical incandescent tungsten lighting.
Illuminant C represents the cooler, blue-heavy spectrum of average daylight. By measuring the gem under both standardized illuminance inside the integrating sphere, you gather incredibly robust data.
Okay, the engineering is brilliant, but I have to push back here as an advocate for the gem cutter. Even with a perfect integrating sphere and fiber optics and standardized daylight illuminance, we are fundamentally dealing with a faceted rock.
What if the stone is highly pleochroic, naturally throwing green and red at the same time?
Right.
What if the master lapidary designed the facet pattern specifically to have brilliant, flashing hot spots of light sitting right next to dark, unlit areas of extinction?
How on earth does a machine with a tiny focused beam size or even an integrating sphere take all that intentional optical chaos and spit out one single unified lab coordinate that accurately represents the human experience of looking at that stone?
You are hitting on the exact nerve of the issue. This raises an incredibly important question, and it is the central, ongoing challenge of gemstone colorimetry.
Arem explicitly acknowledges this physical limitation in the text. He states that for this technology to be commercially viable, the inherent variability of machine color grading must be systematically reduced to less than 5%.
5%. That is an incredibly tight margin of error for something so complex.
It is a formidable, almost impossible challenge. Because of the facet arrangement, a machine might measure a brilliant hotspot on one pass and slightly shift and measure a dark area of extinction on the next pass,
Yielding wildly different lab coordinates for the exact same stone, just seconds apart. So the 5% variance isn't just a minor statistical footnote.
It is the literal battleground for making this technology actually viable and trustworthy in the global market. If the machine cannot consistently read the faceted stone to within a strict 5% tolerance,
the resulting mathematical data is functionally no better, and perhaps even worse, than the highly subjective human eye it is desperately trying to replace.
the ultimate goal of the science is to establish unshakable benchmark coordinate points for specific species, acknowledging that the machine's absolute precision is constantly fighting against the complex physical reality of the cut stone.
Which perfectly sets up the connective tissue for our next transition. We have spent an enormous amount of time building this incredible scientific edifice. We can scientifically identify a stone's atomic lattice and chemical impurities down to the trace element.
We can mathematically plot its exact color coordinates in a 3D Cartesian space using integrating spheres and illuminance A and C. We have successfully quantified the chaos of nature.
What happens when highly funded human laboratories look at all this perfectly compiled data set and learn to replicate it exactly? What happens when a factory builds a crystalline structure, atom by atom, to match the exact chemical formula and the exact lab color coordinates of $1 million ruby?
We cross a terrifying threshold. We enter the era where the natural gemstone market faces a severe existential threat born entirely from its own advanced scientific understanding.
Before we face that threat, let's lock in the practical takeaways for color science. Number 1. You must completely discard 2D opaque color charts when evaluating vivid, transparent gemstones.
They simply do not have the physical or optical capacity to accurately represent gem color.
Number 2, you need to conceptually adopt 3D mathematical color spaces. specifically the CLAB lab coordinate system, to understand how objective, reproducible standardization is being brought to global appraisals.
Number 3. Always account for the physical limitations of the colorimeter hardware itself, specifically regarding how its beam size interacts with the gem's natural pleochroism and its intentional cutting proportions.
Aiming to understand the sheer difficulty of that 5% variance challenge. And your critical thinking challenge. Question 1. How does a mathematical colorimeter, no matter how advanced the integrating sphere is, fundamentally account for a highly pleochroic stone like andalusite that actively and simultaneously displays 3 entirely different colors depending on the viewing axis?
What coordinate does it output? Question 2. What happens to the psychological and financial dynamics of the global gemstone market when color grading variance is universally reduced to absolute zero by perfect machines?
Effectively removing the historical premium paid for a master dealer's expert eye. That is a billion-dollar question that dealers are terrified of. Next.
All right, Chapter 4, the synthetic revolution. This is the final and perhaps most consequential area of Arem's work.
Let's get the big idea for this final chapter.
The core thesis here forces a radical shift in how we analyze gems. It is this: as laboratory-grown materials rapidly evolve to perfectly, seamlessly mimic the physical, chemical, and optical properties of natural gems, microscopic inclusion analysis becomes the final, absolutely crucial frontier of gemological identification.
This is where it gets genuinely scary for the traditional retail gemologist. Let's start the deep dive with nomenclature, because the specific words we use matter immensely here, legally and scientifically.
Arem demands that the industry strictly adhere to the definitions established by the International Committee on Technical Terminology, the ICTT, back in 1974.
We have to meticulously separate the word synthetic from the word homocreate. Let's break those down.
This semantic distinction is absolutely paramount for market clarity and consumer protection. According to the rigid 1974 ICTT definitions, a synthetic material is a human-produced, laboratory-grown equivalent of a naturally occurring chemical compound.
It is not a fake,
Nice.
not an imitation. It has the exact same chemical formula, the exact same internal crystal lattice structure, and the exact same optical properties as the natural mineral pulled from the earth.
A synthetic ruby grown in a factory is a ruby, fundamentally and chemically speaking. The only difference is the geographical location of its birth.
Right. It's a perfect clone of nature. But a homocreate is something entirely different. It's a completely different category of material.
Yes. The term homocreate refers to a laboratory-grown, crystalline material that has absolutely no counterpart in nature whatsoever. It is a completely novel invention of human chemistry.
The Earth has never, in its billions of years, produced this specific compound. However, it possesses physical and optical properties like high hardness and high refractive index that allow it to be faceted and utilized commercially as a gemstone.
Classic examples of homocreates would be things like YAID, which stands for yttrium aluminum garnet, or GGG, gadolinium gallium garnet, or even the ubiquitous cubic zirconia.
They look incredibly like diamonds or colored gems. They act optically like gems. They sparkle brilliantly. But the Earth simply does not make them. They are pure human invention.
Now, let's talk about the terrifying reality that sets in for the standard gemologist working in a typical jewelry store when faced with a true synthetic.
We just spent a massive amount of time building this beautiful, sophisticated arsenal of non-destructive tests, calculating refractive index, measuring specific gravity, analyzing solar spectroscopy, testing thermal inertia.
But against a high-quality, modern synthetic ruby, that entire multi-million-dollar arsenal is suddenly rendered completely obsolete.
It is a devastating, humbling realization for many experienced professionals in the field. Because a true synthetic ruby shares the exact atom-for-atom physical, chemical, and optical properties of a natural ruby pulled from a mine in Myanmar.
Your standard macroscopic tests will simply confirm what the factory already knows, that it is indeed a ruby.
It passes every test with flying colors. The refractive index measured on the refractometer will match perfectly.
The specific gravity density test will match perfectly. The thermal inertia probe will behave exactly the same. The spectral absorption lines viewed through a spectroscope will be identical.
The standard, macro-level instrumentation you rely on daily is practically useless for determining the one thing the market cares about most. Origin. Is it from the Earth or from a crucible?
So we are completely, utterly blind using the macro tools. We have to fundamentally shrink our perspective. We have to abandon the macro and go into the microscopic battlefield.
If the chemistry is a perfect, flawless clone, what is our silver bullet? How do we catch the factory?
Our silver bullet is imperfection. We must look for the microscopic mistakes of the manufacturing process. To do this effectively, the gemologist must abandon the basic jeweler's loop.
And utilize a high-quality binocular gemological microscope, utilizing specialized lighting techniques like dark field illumination, often requiring extreme magnifications of 200x or greater.
At this extreme microscopic level, you are no longer looking at the gemstone as an object. You are looking strictly for the trapped, microscopic fingerprints of the specific environment in which that crystal grew.
You're acting as a forensic investigator, looking for the factory versus the earth. What are we actually trying to spot at 200x magnification? What does a factory fingerprint look like?
You are looking for specific growth markers dictated by the physics of the manufacturing method. In a commercial laboratory, crystals are grown for profit, which means they are grown rapidly.
In the flux melt process, for example, they use highly caustic chemical fluxes like molybdenum or lead compounds to artificially lower the melting point of the gem ingredients.
If the crystal grows too fast, it will occasionally trap microscopic pockets of that unmelted flux. Under the microscope, these look like bizarre, wispy, highly unnatural veils or distinct metallic fingerprints.
Now, what about the older, cheaper methods like the vernal process?
The vernal process, also known as flame fusion, involves dropping fine alumina powder through an incredibly hot oxyhydrogen torch. The powder melts and drips onto a spinning pedestal, slowly building up a cylindrical crystal called a boule.
Because the boule is spinning as the liquid crystallizes, it leaves behind microscopic, concentric, curved growth striae. It looks like the curved grooves on a vinyl record.
Nature absolutely never grows crystals in perfectly curved lines. Nature grows in flat, angular planes. If you see curved striae at 200x, you are looking at a factory product.
You might also spot perfectly spherical gas bubbles, which indicates a rapid boiling melt process, another hallmark of the factory. And how does all of that factory evidence compare to the fingerprints of nature?
A natural gem forms over millions of years in a highly chaotic, slow-cooling, tectonically active environment deep underground. Instead of remnants of factory flux or perfectly spherical gas bubbles, you will see the scars of geological time.
You will see natural healing fissures. What does a healing fissure look like?
Imagine the crystal fractures deep underground due to an earthquake. Over thousands of years, mineral-rich hydrothermal fluids seep into that crack and slowly crystallize, healing the fracture shut.
But the healing isn't perfect. It traps tiny, angular, highly irregular droplets of that ancient prehistoric liquid inside the stone forever. Those are natural inclusions.
You also see solid inclusions of entirely different, completely formed minerals like a tiny, perfect, needle-like crystal of rutile, or a microscopic block of apatite that got caught and physically trapped inside the sapphire as it slowly grew around it.
The factory desperately tries to create flawless perfection. Nature, thankfully, always leaves a messy, chaotic, highly identifiable signature.
If we connect this microscopic battle back to the broader economic picture of the trade, this technological arms race is everything. The factory employs brilliant chemists to constantly create cleaner, better synthetics without curved striae or flux veils.
The gemologist responds by needing more powerful microscopes, better lighting, and chemical analysis at the atomic level to find the increasingly tiny microscopic fluxes. This constant high-stakes arms race is exactly what prevents the total catastrophic collapse of the natural gemstone market.
Think about it. If the day ever comes when a factory can replicate not just the perfect chemistry, but can intentionally replicate the natural chaotic inclusions perfectly, the entire historical and economic concept of natural scarcity completely evaporates overnight.
Which perfectly encapsulates the connective tissue of this entire journey we've taken today. This final microscopic frontier of inclusion analysis represents the absolute peak of our historical and scientific evolution in gemology.
Think about where we started. We began with chaotic, ancient naming conventions based on myth, folklore, and subjective color. Then we moved into the rigorous era of precise chemical identification and complex atomic solid solution theory.
We fully embraced mathematical, machine-driven color grading, using integrating spheres to permanently remove human bias. And now, at the end of the text, we find ourselves in an era where human ingenuity in the laboratory has become so staggeringly advanced that it forces the gemologist to look closer than ever before.
At 200x magnification in dark field illumination, just to find the truth of a stone's origin. The ultimate beautiful irony of modern gemology is that our most advanced million-dollar scientific tools are now primarily used to identify and verify the microscopic flaws of nature.
Simply to prove historical value. Let's run through the final highly practical takeaways for navigating the synthetic revolution. Number 1. As a professional, strictly enforce the legal and scientific nomenclature difference.
Always know when you are dealing with a precise chemical clone, which is a synthetic, versus a purely manufactured, completely novel invention, which is a homocreate.
Number 2. Never ever rely solely on your standard macroscopic optical or thermal tests like the refractometer or the thermal probe to distinguish high-quality modern synthetics from naturals.
Those tests will essentially lie to you by confirming that the chemistry is correct. Number 3, you must dedicate yourself to mastering high magnification inclusion analysis at 200x to identify the microscopic fingerprints of rapid laboratory growth environments versus the chaotic, beautiful, natural healing fissures of the Earth.
And your final critical thinking challenges to wrap up the text. Question 1. If a homocreate material, say a highly advanced form of cubic zirconia, is manufactured in a lab to possess optical beauty, brilliant dispersion, and physical durability that is objectively, scientifically superior to absolutely any natural gemstone ever pulled from the earth.
On what historical, psychological, or economic basis should the global market value it? Should perfection be cheap?
Question 2. When synthetic manufacturing inevitably evolves to the point where it can perfectly, intentionally, and economically mimic natural chaotic inclusions like rutile silk and healing fissures, rendering the microscope useless, what is the next theoretical frontier for gemological testing?
How do we prove a stone is natural when the clone is physically indistinguishable from the original on every level?
So after this intense masterclass, what does this all mean for you, the historian, the enthusiast, the researcher? You've sat with us through the dense mathematics of solid solution series, the physics of Fraunhofer absorption lines, the 3D Cartesian coordinates of lab color spaces, and the microscopic hunt for unmelted fluxes.
Hopefully, we've successfully torn down the romantic, outdated facade of the precious gemstone hierarchy and replaced it with a rigorous, cold, brilliant, and infinitely more fascinating scientific reality.
I certainly hope so. And I want to leave you with one final provocative thought, a puzzle drawn directly from the underlying tension present throughout Arem's text.
A natural gemstone's traditional historical value relies almost entirely on its natural scarcity, the incredibly improbable geological lottery of its violent creation deep in the earth.
But as human laboratories construct increasingly perfect, flawless synthetics on demand, and as our advanced colorimeters standardize and sanitize color into flawless, reproducible mathematical grids, will the entire future of gemstone valuation actually invert upon itself?
That is a profound question to think about. Will we end up in a market where absolute, flawless optical perfection is considered cheap simply because it is easily manufactured by a machine?
Will we end up fundamentally prizing the flaws? Will the future market pay a massive, astronomical premium for the highly irregular inclusions, the asymmetrical color variations, and the evidence of internal structural strains?
Simply because those natural imperfections are the literal only things a machine cannot authentically replicate. Will the geological bruise eventually become vastly more valuable than the perfect beauty?
The bruise becoming more valuable than the beauty. That is a phenomenal thought to end on. From the incredibly muddy diagnostic waters of the medical X-ray machine analogy we started with, down to the painstaking microscopic hunt for a tiny healing fissure at 200x magnification.
The true value, ultimately, isn't found in the pristine perfection of the laboratory. The value is entirely contained in the microscopic proof of the Earth's chaos.
Thank you for joining us on this highly technical, rigorous deep dive into the science of gems. Keep looking closely at the world around you, keep demanding the empirical data, and keep questioning the history of the world beneath your feet. Until next time.